Hello everybody, welcome to my YouTube channel Easy Mathematics. Hope you like my previous video of Rolle's theorem. Now we are going to discuss about the Lagrange mean value theorem. This is nothing but the extension of the Rolle's theorem. In Rolle's theorem, we know there are total 3 conditions. Here in the Lagrange mean value theorem, we have instead of the 3 conditions, the last condition is absent. That means only first 2 conditions are valid here. So what is the statement at first? Let us see. So if the function is defined on a closed interval AB in such a manner that fx is continuous for all x in AB, closed interval AB, and the derivative of the function exists for all x in the open interval AB, then there exists at least one value C lies in between A and B such that f of p minus f of a divided by b minus a is equals to f dash c. Just compare with the Rolle's theorem, you will find out that f of a is equals to f of b. That condition is absent here. That means if geometrically we want to analyze the theorem, then we will find out that in case of the Rolle's theorem, this 2 points should be same. That means these endpoints are equal. But in case of the Lagrange mean value theorem, we will find out that this is our FA and this is our FB. These 2 values are different. So if these 2 values are different, then these 2 points, if we join by a straight line, then we will find out a second line. So now what happened? The given function is continuous and definitely it is differentiable everywhere within the given interval. Now if this one is the situation, then we will find out a C. C means we will find out in between these 2 values A and B, definitely there exists at least one C. Remember, this is at least, that means more than 1 point always can be possible to exist. So there exists at least one point where if we draw the tangent, that means at this point if we take the derivative, then this derivative value is definitely parallel to this line, this second line joining by A and B. These 2 points if we join by a straight line, then at that particular point we will find out a tangent which is parallel to this one. So just look, this value means what you know. This one is actually here, the entire this value is f of b and this one is f of a. That means we can say this portion is f of a and this entire portion is f of b. So that this portion, only that much is f of a minus f of b minus f of a, is it not? And this length is nothing but b minus a. This entire length is nothing but b minus a. So that what should be the value of this one? This one we can say that f of p minus f of a, this is the, we can say this is the perpendicular and this is the base. So perpendicular by base means it is nothing but the tan theta, and tan theta is nothing but the derivative of the function, is it not? That's so why the formula is here for the mean value theorem is fp minus fa divided by b minus a is equals to f dash c. That is verified. So this is our Lagrange mean value theorem and this one its geometrical interpretation. I hope you can understand how the Lagrange mean value theorem applied over the real-time example. Let us apply the Lagrange mean value theorem. This is MVT, mean value theorem, for the function this one. So what is the function? Fx is equals to x minus 1 into x minus 2 within the interval 0 and half. So the given function is definitely a polynomial function. So as it is a polynomial function, it is continuous and differentiable everywhere for the real x value. So the given function fx is x square minus 3x plus 2 and it is continuous within the interval 0 and half and definitely differentiable on the open interval 0 and half. Again, the derivative of the given function we will find out as it is 2x minus 3. So this one, and at the end point, that means f0 the value is 2 and f of half the value is 3 by 4. We should require the value because our formula for the Lagrange mean value theorem is f dash c is equals to fb minus fa divided by b minus a. So now this is our mean value theorem, and if we apply, that means if we substitute all those values, then we will find out that the c value is 1/4. All the conditions of mean value theorem is verified for this given function, and hence we conclude that definitely there exists a c. This c value is here, it is 1/4. For at this point we will find out a tangent which is parallel to the value line joining the point a and b, that means which are the end points of the function. These 2 points, if we join by a straight line, then we will find out a tangent which is parallel to that particular line. So the Lagrange mean value theorem is verified for this given function. Let us do one more example. So the function is fx is equals to log x, and now the limit is 1/2 to 2. So the log function is again continuous and differentiable for all x within the range 0 to infinity. Okay, now so it is a positive function actually. So that fx is continuous within the given range, given closed interval, and differentiable within the open interval, and its derivative is, we know, that is 1 upon x. So its derivative value is known. Now if we substitute the Lagrange mean value theorem, that means if we take the Lagrange mean value theorem and substitute all those values, then we will find out that the c value is 3/2 log of 1 upon log 4. So this value is definitely lies in between 1/2 and 2. If you want to verify, then for your reference I can say that log 4 base e, its value is 1.3863. You can verify it from the log table also. So if we substitute all those and calculate, we will find out the value of c lies in between these two. Hence the Lagrange mean value theorem verified, and we will find out a particular c within the given interval. One more example let us consider. If a and b are distinct real numbers, then so that there exists a real number c between a and b such that a square plus ab plus b square is equals to 3c square. So here what to do? Let us define the function x cube first, and which should be defined within the range a and b, closed interval ab. After that, if we take the derivative of this function, then it is 3x square. This one is a polynomial function, so it is exist within the range a and b. Now we can apply the mean value theorem here. So if we apply the mean value theorem, then this is the formula, and if we substitute all and simplify, then we will get a square plus ab plus b square is equals to 3c square, which is our required proof. Hence the proof. Now one more question let us do. So it is f dash x is 0 is given in the interval ab. Then so that fx is a constant function in ab. So derivative is 0 within this interval, and our requirement is to show that fx is a constant function. So what to do? So at first let x1 and x2 be two arbitrary points such that these 2 points lies in between the interval a and b. Then we apply the mean value theorem, and within the range x1 and x2, what we will do? We just apply the mean value theorem within the range x1 and x2. So within this range, this is the formula for the mean value theorem. So definitely c lies in between x1 and x2. According to the given condition, within this range, this derivative value is 0. So that what we will find out from here, that we'll find out that this one 0 means this one multiplied by 0 means 0, and we will get f of 2 is equals to f of, that means f of x2 is equals to f of x1. So x1 and x2 are two arbitrary points, and they are different, lies within the interval ab. So it follows that the fx is constant in ab. Is it not? Otherwise, how at two different points the functional values are same? Unless it is a constant, it is not possible. Hence the proof. One more very important example is here, and the problem is if f dash x exists and if dash x less than 0 everywhere in a open interval AB, then so that fx is a decreasing function in AB. So now what to do? Again we consider the two arbitrary points within the interval AB in such a manner that x1, x2 entirely lies in between AB. Now applying Lagrange mean value theorem within the interval x1 and x2. So this is the formula for the mean value theorem, and according to the given condition here f dash x is less than 0 everywhere. That's why we can say that one is less than 0. Now as this one less than 0, so we can say from here that x2 minus x1 is always greater than 0. Is it or not? Because just look at the limit here, x1 less than x2 is given. That's why x2 minus x1 always greater than 0. So that part is greater than 0. So if this inequality holds, that means what? That portion should be less than 0. That means x2, f of x2 less than f of x1 whenever x2 is greater than x1. Hence, from here we can conclude that the given function is a decreasing function in AB. I hope you understand all those questions. Now we are going to give one more different form of the Lagrange mean value theorem. What is that form? That is actually nothing very special, but just changing the interval. Previously we have started from the interval a comma b. Now we have changed the interval as a comma a plus h. So just the interval is changed and the rest is same. Then what happened? F is continuous within this closed interval. F is differentiable on the open interval a comma a plus. Then f of a plus h, instead of b we should substitute a plus h, is equals to f of a plus h into f dash a plus theta h, where theta lies in between 0 and 1. Just remember that our form is f of b minus f of a divided by b minus a, is it not? So that one is equals to f dash c. That one is equals to f dash c. Now what happens here? F of b, instead of b we substitute a plus h, so that we will write down here also a plus h, so it is only h. So that h if we multiply we will find out this term. Instead of c we substitute a plus theta h. Now we can write f of a plus h is equals to f of a plus h into f dash a plus theta h. So now instead of the interval, if again we change the interval as 0 comma x, then this above form we will find out as fx. Instead of a plus h we should substitute x, and instead of a we should substitute 0, so that this one becomes f of x is equals to f0 plus x into f dashed theta x. This particular form is known as the Maclaurin's formula. Okay, so just this different form of Lagrange mean value theorem, we do one more example here. So what is this? The mean value theorem. Just use mean value theorem to prove this inequality. What is the inequality? 0 less than 1 by x log of e to the power x minus 1 by x less than 1. So what to do? Here at first let fx is equals to e to the power x. Then from the mean value theorem, this form if we apply, then we can write directly fx is equals to f0 plus x into f dash theta x, where theta lies in between 0 and 1. Now given fx is equals to e to the power x, so that we should substitute here e to the power x. At the point 0 it is e to the power 0. So x into at the point its derivative is again same e to the power x, and at the point theta x it is e to the power theta x. So now if you simplify, then we will find out theta is equals to 1 by x log of e to the power x minus 1 by x. We know theta always lies in between 0 and 1. Hence from here we can say this entire value lies in between 0 and 1, and which is our required proof, and hence the result. So if you understand it properly, then one question is here for you, That is your do by yourself question. Hope you able to do this one. So the question is, prove the inequality x divided by 1 plus x less than log of 1 plus x less than x if x greater than 0. Do this question and answer for this question in the comment box. And if you have any doubt regarding the topic, then you should write in the comment box also. So have a nice day and thank you all.